Welcome to my talk about nonlinear robust optimization. I'll talk about an adaptive bundle method and an auto-approximation method, and the content I present is based on joint work with Frauke Liers and Michael Stingl. We'll take first a look at the setting of nonlinear robust optimization with the notion of inexactness. I'll present an adaptive bundle method for the setting, and we'll see how to apply it to the robust gas transport problem, even with discrete continuous decisions using an auto-approximation method. First, we see here the setting of nonlinear robust optimization, where we have a decision variable x and an uncertain parameter u, so this constraint should be fulfilled for every possible realization of u. For this type of problem, there are some reformulation approaches, but usually they require restrictive assumptions such as linearity or convexity. And we want to consider a very general setting. So we want to solve this min-max problem. That's how we formulate the robust optimization problem. And one major challenge here is in the presence of non-convexity especially, even to evaluate one possible decision x, as this requires to find a global solution to the adversarial inner problem. So we want to tackle this problem via an adaptive bundle method. So what we do is we see this problem as a min-max problem, as a non-smooth optimization problem. So we have a minimization problem with the optimal value function of the inner problem as non-smooth objective function. And for this, we want to use a bundle method for this non-smooth optimization problem. And in order to evaluate the optimal value function of the inner problem, we will later use a piecewise linear relaxation approach. And using this approach, we can approximately solve the inner problem. And the advantage of this approach is that we have a guaranteed error bound for the error we have here in the optimal value function. But the drawback is that we still have an error, so we cannot exactly solve the inner maximization problem. So let's see what type of inexactness that we have to consider. So we have this minimization problem with objective function, that is the optimal value function. And we have a bounded error in the function value of this optimal value function. So when we want to use an adaptive bundle method or a bundle method, we have an approximation of the function value. But in order to use a bundle method, we do not only need access to function values, but also to subgradients. And usually one uses the Clark subdifferential in the context of bundle methods. In our case, where we have an optimal value function as objective function, the Clark subdifferential is computed as it is written here. So that's illustrated here in this picture, where we have that each black graph denotes the function v for one fixed parameter u. So in the bold line here denotes the optimal value function then, the objective function f. And at this example point x, we have in this convex hull here two subgradients, namely the subgradients with respect to x for the active worst cases u. So we have the convex hull of these two yellow subgradients as the Clark subdifferential. But in our case of inexactness, we may have access only to the worst case or the inexact worst case that corresponds to this black graph. So we may have access only to this inexact subgradient. And that's what we use as an approximation of the exact subdifferential. We use the convex hull that describes the exact subdifferential, but we do now also consider inexact worst cases and add them to this convex hull. And we see already here that our inexact subgradient may be far away from the exact subdifferential, as here we have a only negative subgradients in the exact one, and we even have a positive in the inexact one. So we have to find or develop a bundle method that is suitable for this type of inexactness. But first, let's see what's the general idea of bundle methods. Bundle method is usually used in order to minimize a non-smooth function, and this is done by approximating the function by a cutting plane model. So in each iteration, one solves the piecewise linear model, that approximates the original function. One adds a proximal term and then finds new trial iterates. So there are bundle methods that can even handle non-convexities. And here in this picture, we see an illustration of the technique that is used for the case of non-convexities. This is the downshift mechanism. So what we do is when we have a series iterate here, for example, and a trial iterate here, and there is a subgradient that should be of help to generate a cutting plane that corresponds to this trial iterate. And when this overestimates the function value of the series iterate, then we downshift the cutting plane such that the model is still valid around the series iterate. And when we want to consider non-convexity, we usually consider a certain relaxation of convexity. In the context of bundle methods, this is often epsilon convexity or then approximate convexity. So let's first define epsilon convexity. It is a relaxation of convexity that is defined by this inequality. And this reminds us of uniform convexity, but we have the plus here instead of a minus as it is a relaxation of convexity. Now, one useful implication of epsilon convexity is that this subgradient inequality is still fulfilled. So we have a subgradient inequality with a distance-dependent arrow, which is illustrated in this picture here, where we have here the subgradient, and we know that the function lies still above this distance-dependent arrow plus the original subgradient. And we now can define approximate convexity, which says that for every x and every possible epsilon, there should be a region around x such that epsilon convexity is fulfilled. And this is now the assumption that we use in the following. So there are bundle methods that can handle approximate convex functions, even in the presence of inexactness. For example, there's the bundle method by Null, which is suitable for approximate convex objective functions and inexactness in function values and in subgradients. The type of inexactness for function values says that there is a constant error bound on the distance between inexact and exact function value, and the same type of inexactness is considered for the Clark subgradients in Null's bundle method. So he assumes to have a bounded distance between inexact subgradients and the exact Clark subdifferential. And in his convergence proof, he then makes use of this bounded distance. As under the assumption of epsilon convexity, one has this subgradient inequality with a distance-dependent arrow here, and having the bounded distance of inexact and exact subgradients, we have another distance-dependent arrow so that in total one derives a distance-dependent arrow in subgradient inequality. And this is then one key inequality that is used by Null in order to prove convergence of his bundle method. So let's come back to our case where we had no constant error bound on the distance between inexact subgradients and exact subdifferential. So remember, we had a constant bound on the arrow that we have in the objective function value, but we did not have this constant error bound on the distance of subgradient. So what we have is this approximate function value and the corresponding subgradient, and this combination does not fulfill the assumptions in the bundle method by Null. So we have to generalize the bundle method. But let me mention here that we did not restrict ourselves to a certain choice of tool in order to obtain this inexact worst case, or this inexact function value and subgradients. So we now want to generalize the bundle method by Null, and we do this as follows. We use our inexact subdifferential, And let's first have a look at subgradient inequality that is ensured by our approximate subdifferential. So we have this subgradient inequality that is still fulfilled. Under the assumption of epsilon convexity, we have still this distance-dependent arrow and another constant arrow that is the function value arrow at the point of interest, at which we evaluate the subgradient inequality. And in order to use Null's convergence proof or to obtain a similar key inequality, we would like to have distance-dependent arrow here. So what we do is that we let the arrow in the function value depend on the current distance of trial and series iterates in the bundle method. So we use this inexact function value, the corresponding subgradient, but this arrow in the subgradient inequality now is distance dependent using trial and series iterates. So when we evaluate the subgradient inequality at a pair of trial and series iterates, and that's actually where the subgradient inequality is of interest, then we have a distance dependent arrow. And this enables us to generalize Null's convergence proof. So what we do in the end is to use his bundle method, plugging in our adaptive function value approximation and the corresponding subgradient evaluation, and we obtain a converging bundle method. Where at the solution, then again, the 0 is in the approximate subdifferential, which implies this subgradient inequality with the arrow in the function value here. So to sum this up, we have assumed to have access to an inexact worst case in the context of nonlinear robust optimization to the corresponding function value approximation and subgradient approximation. And then we were able to prove convergence of the resulting adaptive bundle method under the assumption of approximate convexity. For this, we let the exactness parameter also depend on the current distance of trial and series iterate, and that's how we obtain this convergence result. So we tested this method for the robust gas transport problem, where we consider a stationary setting of gas transport and we want to minimize the cost of transport. So the problem is depicted here. We minimize the cost of compressor control, and physical constraints are to fulfill flow conservation and pressure loss should be fulfilled. So the difficulty of this problem lies here, where we have non-convexities, as we have this non-convex pressure loss constraint. And now we want to consider uncertainties, where a natural choice are these pressure loss coefficients, which are difficult to measure in reality, and demand that cannot be foreseen. And reformulating this problem with uncertainties, we obtain this min-max problem here. So we have moved the pressure bounds to the objective via penalty term, and we have here the physical constraints. And in our bundle method, we now need to have access to an approximate solution of this problem. And we do this by using piecewise linear relaxation for this pressure loss constraint. And an error in this pressure loss constraint results in an error in the optimal value function. But in practice, this relation of this error bounds is not very tight. So what we do is that we allow for a large error here and then adaptively refine the relaxations in case of a too large a posteriori error. And we tested this approach, so this piecewise linear relaxation approach, in the adaptive bundle method and tested it for realistic gas lib instances, where we have here results for a network with 40 nodes and 6 compressors. And we compared here the results for different values of the exactness parameter. And to judge the quality of the solutions, we can look at the aggregate subgradient, which in the convergence proof is proven to lie in the approximate subdifferential at the solution. So we see that here for the small exactness parameter, we obtain good solution, but for this large one, it's a worse solution. And we see here in the last column that by letting the exactness parameter also depend on the current distance of iterates, we can improve the results without needing much more running time than in this example. So we need here more iterates or more function evaluations, but especially in early iterations, we can allow for a large error so that we do not need much more time and still obtain results that are comparable to these ones. So in the context of gas networks, it would be interesting to consider also discrete decisions, as for example for compressors, one usually has a passive mode or strictly active mode, so that we have a variable with a disconnected domain here. Or another case are valves, which could be open or closed, so one wants to be able to model a binary decision here. And when we want to consider such discrete decisions, we obtain a mixed integer nonlinear robust optimization problem of this form with uncertainties here in the U. So this type of problem is now even more challenging than the continuous version. And in order to handle this type of problem, we want to consider an auto-approximation method that uses the adaptive bundle method for the continuous subproblems. So what we consider now is a mixed integer nonlinear robust optimization problem. And now we restrict ourselves, as we are in the context of an auto-approximation approach, to the convex case. So we consider this type of problem with a robust constraint here, where we maximize over the uncertainty set. And we want to apply an auto-approximation method to this non-smooth MINLP. And for the subproblems, which are solved in order to obtain linearizations of the constraints, we want to use our adaptive bundle method. As the continuous subproblem as well as the feasibility problem now have the structure of the problems which can be handled by our adaptive bundle method. But still we want to consider inexactness in the evaluation of the worst case. So we have seen that this is not a problem for the adaptive bundle method, but now let's see what type of inexactness we still have in the result of the bundle method, and which has to be considered in the auto-approximation method. So we have again a bounded error in the function value, as we have an inexact worst case at the solution of the bundle method. And what we also obtain is an inexact subgradient, which when we evaluate the subgradient inequality at the inexact function value, still underestimates the correct function. So this function value and subgradient approximations can be used to generate linearized constraints in the auto-approximation method. And here we have such an inexact linearized constraint, which is still valid. But one drawback is that as you have this underestimation, we now may accept infeasible solutions in the auto-approximation method. So summing this up, we have these inexact cuts, these valid underestimators that accept approximately feasible solutions. So that's how we can adapt the proofs from existing auto-approximation methods. And then we were able to prove convergence of our auto-approximation approach with approximately feasible and approximately optimal solutions. And one key point here was to prove that the adaptive bundle method not only solves the subproblems, the continuous subproblems, but also can be used to generate suitable subgradients. And we did some first test runs for GasLib40 instance, the gas network instance with 14 nodes. And we see here already that the main part of the running time is spent by the bundle method. So One further research question here would be how to recycle cutting planes and allow for a warm start of the bundle method. So let's sum up what we have seen in this talk. We have seen how an adaptive bundle method was developed for the setting of nonlinear robust optimization in the presence of non-convexities, and how the difficulties were handled by an adaptive approximation of the function value, of the optimal value function. And for the convex setting, we have seen that we can even include discrete decisions in our setting. So we have developed an auto-approximation approach that uses the adaptive bundle method for the subproblems, and how inexact cutting planes can be handled there. And one further research question here will be to make full use of the adaptive bundle method's capability to handle non-convexities. So the next step will be to extend this to quasi-convexity. That's how I conclude my talk, and I thank you for your attention.